Hello everyone. This video lecture is about the binomial probability distribution, which is going to be something that's going to be very useful for us when we try to calculate various probabilities. So our goals for this lecture will be to identify binomial setting. It's usually certain characteristics that the binomial distribution must meet. We're also going to look at a probability of an exact event, so for example exactly 2 heads, and we're going to look at the probability of a fewer than event, so for example fewer than 3 heads. We've already been doing binomial probability questions in class, you just may not have realized it. The use of the formula will actually speed up our work quite a bit. So the binomial setting is a list of conditions that have to be met before you're allowed to use this formula. So for example, we need to make sure that the experiment consists of a fixed number of trials. We'll use the letter n to represent the number of trials. Each trial will only have 2 possible outcomes. Usually we describe those possible outcomes as either a success or a failure. Now, a success does not necessarily imply a positive outcome, nor does a failure necessarily imply a negative outcome. Success just means that we've met the defined objective. So for example, in coin flipping, maybe our defined objective is we're interested in heads. So we would identify heads as a success, tails as a failure. In an insurance example, we might look at a defined objective as a major claim. So in this case, a major claim is a success, where no claim is a failure, which seems a little bit backwards from the way it ought to be. It's just the way we describe it. Each trial in the experiment does need to be independent. That is, if I observe one outcome in a given trial, we're not going to change the likelihood of the outcome in the next trial. And that's reflected in the next condition. The probabilities of both outcomes, success and failure, are constant throughout the experiment. That is, they remain the same. This is a lot of information to remember, and you're going to have to justify that this setting has been met on an AP exam. So one of the easiest ways for us to remember this is to use an acronym, FITS. So the F represents the fixed number of trials, I represents independence, T represents 2 possible outcomes, and the S is that the probabilities remain the same throughout the experiment. So anytime you encounter a situation where you feel inclined to use the binomial probability, you're going to need to make sure that you show that these conditions have been met. So this is the function we're going to end up using. The probability of R successes in n trials can be expressed by, and here's our formula. So you'll see n and then an r. There's no fraction bar there, and I'm going to talk about that in a moment. And then you have p raised to the n power, q raised to the n minus r power, where p is the probability of success and q is the probability of failure. One really important thing to realize is sometimes we don't always express this formula with a q. Instead, sometimes we use 1 minus p. So a success and a failure in a binomial problem is going to be a pair of complementary events. So if you're rolling a 6-sided die and the event you're interested in is rolling a 6, then the probability of failure is going to be 1 minus the probability of rolling a 6. So those events are complements. This n over r piece is something that's pretty interesting. Most of you are probably used to seeing this in a slightly different way. This stacked number, stacked fraction, can be represented using this expression with the factorials. So n factorial over the quantity n minus r factorial times r factorial. You are probably used to seeing it like this. So your calculator can help you out. This is a combination. Interestingly enough, though, the notation in red, NCR, actually comes from the calculator. And when you see that in a textbook, it's because the textbook has taken the easy way and has decided to adopt calculator notation over the correct mathematical notation, which is the n over the r. So let's look at our first problem, and like with many things with probability, we'll start off with some pretty easy events. So I'm going to be interested in calculating the probability of exactly 2 heads on coin flips. So in this particular case, the coin will be tossed 6 times. You're asked to determine the probability of 2 heads. So our fixed number of trials is 6. In this case, we do have independence. And we know that this is independent because if I flip a coin and I get heads, a coin has no memory, so it doesn't change the likelihood that I'll get heads the second time. We have two outcomes, and in this case it is heads or tails. And for our question here, heads would be a success. And then finally, same probabilities. So in this case, we know that the likelihood of getting heads isn't going to change. The likelihood of getting tails isn't going to change. We don't introduce a coin with a different number of sides after the first couple of trials. So as far as I can tell, that this fits the binomial distribution. Now we're going to have some shorthand for the binomial distribution, just like we did for the normal distribution. So you'll still have your twiddle, and you'll have a capital B for binomial. And the two quantities that this shorthand accepts is n and p. N being the number of n being the number of trials, p being the number of successes. So this is a binomial distribution where n equals 6 and p equals 0.5. So the question goes on to say that a fair coin is just as likely to land heads as it is to land tails. So n equals q, which equals 0.5. Apply the binomial probability function. So with many things, I would always advocate for starting off with writing out the formula without substituting any values first. The reason we do this is it helps us to remember the formula, and it helps anybody grading your work, like an AP exam grader, know that you knew what the correct formula was, and if you make a mistake after this point, it's probably due to a mistake in substitution. So there is our formula. Now, in this case, we have 6 trials. We're interested in 2 successes. The probability of success is a half. And we have 2 successes. Then probability of failure is a half. And we have 2 fewer failures than we have trials. So we have n minus r, or 6 minus 2, which gives us 4. So ultimately, that is the equation that we are attempting to solve. Now, we're going to have to take care of that coefficient at the beginning first, so that combination. You could pull out your calculator at this point to do that, or you could calculate it by hand. So we would have 6 factorial over 6 minus 2 factorial times 2 factorial, which would simplify to 6 factorial over 4 factorial times 2 factorial. Now, if you've never broken one of these down before, the 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Our 4 factorial is 4 times 3 times 2 times 1, and our 2 factorial is 2 times 1. So my 4 factorial and a big chunk of my 6 factorial divide to give me 1. So now all I'm left with is 6 times 5 divided by 2, or 15. So now I can substitute that piece into my equation. I have 15 times a half to the second power times a half to the fourth power. And now we've reduced this to a calculator question. I can type that into my calculator, and I get a probability of about 23%. Another thing that we're going to need to calculate when we're working with the binomial distribution is not just the likelihood of a certain number of successes, but maybe a range of successes. So in this particular problem, I'm interested in calculating the probability of 3 or fewer. So the probability I'm calculating looks like this. And one of the things that we remember from our probability unit is when you have a union or an OR probability, we're going to have to use the addition rule. So ultimately, we're going to find the probability of 0 heads plus the probability of 1 head plus the probability of 2 heads. So really, we have 3 of these to calculate. So we'll begin with 0. So it's the same scenario as before, so there's no need to check the binomial setting. If this was the AP exam, you would probably just make a note that it fits the binomial setting as the previous step shows, or something along those lines. And again, I would begin with probably writing out the formula. So the probability of our successes is n, choose r, times the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So in this particular step, we're interested in the probability of 0 heads. So we have 6, choose 0. Probability of success is still a half. Number of successes is 0. Probability of failure is still a half. And the number of failures would be 6. Now, we know that anything raised to the 0 power is equal to 1. And if you have 6 objects and you choose them 0 ways, that also becomes 1. So we end up with 1 times 1 times a half raised to the 6th power. So we get to see that this probability is about 1.5%. We can use the same method to then determine the probabilities of r equals 1 and r equals 2. The only thing that you're changing is different things are getting substituted in. So let's go ahead and look at each of the next 2 probabilities. Let's start with the probability of 1 head. So in this one we have 6, choose 1. Probability of success is a half, and we're going to have 1 success. Then the probability of failure is still a half, and now we have 5 failures. When we look at the combination for 6, choose 1, we see that you can choose 1 6 ways. You have half to the first power, or just a half, and then a half to the 5th power. So the probability that you'll get 1 out of 6 is going to be about 9.38%. Now for our final probability for this problem, we're looking at the probability of 2 heads. So now we have 6, choose 2. Probability of success is a half. With 2 successes, that means we are now down to 4 failures. And when you do 6, choose 2, you'll find there's 15 ways to choose 2 from 6. Then we have a half to the 2nd and a half to the 4th. The probability for this one ends up being about 23.44%. So when we add all of these together, the probability of getting 3 or fewer heads on 6 coin tosses is going to be about 34.4%.